Warwick, random walks in groups, amenability and ratio limit theorems.
Okay, thank you. Well, thanks very much for inviting me here and giving me an opportunity to speak. So what I'm going to talk about is joint work with Rhiannon Dougall. Who is that? Darwin University. Okay, so it's going to be really about random walks on groups rather than dynamics, but I might talk about a bit of dynamics at the end. So setting is going to be that G is a countable group with, let's say, E is the identity element. And we're going to have a random walk on this group. So that's going to be given by a probability measure. So let's call this mu. So mu G to R plus probability measure. So obviously it's a function that sums to 1. And then that gives you a random walk. Given by random walk on G, given by the probability that, well, let's say that where you are at time n is denoted by Sn, so that if you're at time n minus 1 at some element h, that you move then to hg, that probability is given by mu of g. Okay, so we need first of all to make some kind of an assumption that this is non-degenerate, so that this isn't supported on some smaller subgroup. Okay, so always assume generate. Then more formally, that's the support of mu, which is a set of G for which mu of G is positive. Let's in fact that this generates G not just as a group, but as a semi-group. Okay. So just as a trivial example, if we have the integers, if you just had the number 1, that would generate it as a group, but it wouldn't generate it as a semi-group because you could only go forward. So we need somehow invert in there. We're not necessarily assuming that the support is symmetric, but we do need some inverse so that we just generate without having to throw inverses in. And so you could think of this in some sense as the random walk explores the whole group. So yeah, eventually you'll get everywhere. Okay, and then we have the notion of convolution. So mu star nu, that evaluated at G is going to be the sum over group elements H, mu of H, nu of H inverse G. And then we're going to be particularly interested in this quantity, mu convolved with itself n times, evaluated at G, because in probabilistic terms, that's the probability that at time n you are at G, given that you started at the identity. And we're going to be interested in particular this where we take the identity, so starting at the identity, coming back to the identity in n steps, and we'll define a growth rate associated to this, so we'll call this lambda. So something that depends on the group and on the lambda walk. And this is the limit surplus n goes to infinity of mu star n of e to the 1 over nth root. Okay, so again, this is the probability that starting at the identity or back at the identity in n steps. This is a limit surplus, not a limit, because quite often, well, just as an example, if you take a simple random walk on the integers, where you're stepping +1 probability a half, -1 probability a half, you can only get back to the identity in an even number of steps. So for odd n, this would be 0. So we want to take the limit up here. And this is always going to be less than or equal to 1. So what more can we say about it? So really we're going to be interested in when this is actually equal to 1 and when it's less than 1, so the probability is decaying exponentially fast. Let's just think about some examples first. And the first one indeed, let's just take the integers and simple random walk. So mu of 1, mu of -1 is 1/2. Simple random walk. And so then probability of getting back to 0 in 2n steps. Well, you'll have to have taken as many steps to the left as you do to the right. So out of the two to the 2n probabilities, it's going to be 2n choose n that will give the ones with the same number of plus and minus ones, and then to the probability you divide by 1 over 2 to the 2n. And you can work this out, and you can work this out exactly as asymptotically using Stirling's formula. But let me just say that it's going down like 1 over root n. Okay, so in particular here, the lambda is equal to 1. Okay, then we could just increase the dimension. So example 2 would be to take z to the d, and again we'll have simple random walk. So mu of any unit vector like this, so it's going to be all zeros, etc. Will have a plus or minus 1. that's going to be 1 over 2d. So again, you've got the power issue that if you start at 0, you can only get back to 0 in an even number of steps. But then you have that probability of doing that. Well, it's a bit more complicated, but we don't say equal, we want to say comparable. It's going to be 1 over n to the d over 2. So it's going down faster, but still only at a polynomial rate. So again, you've got lambda equals 1 in this example. And then for third example, let's say the free group on 2 generators. So really kind of at the other extreme. So say this is generated by symbol A and B. Okay, and again, it'll be simple random walk. So we'll give probability 1 quarter to each of A inverse, B, and B inverse. Again, if you start at the identity, get back to the identity, you need to have an even number of steps. But now it's harder to get back. I mean, if you compare this with z squared, where there's lots of ways you can go back by just kind of looping around, in the free group, there's no loop, so you've got to, for every path you go out, you've got to go back along that path. Okay, so we'd expect the probability to be smaller, and indeed, what you get, well, not equals to comparable to, it turns out, 2 square root of 2 over 3 to the 2n, and then there's a n to the minus 3 over 2 factor, which doesn't really worry us. And this number here, this is approximately 0.94, so it's less than 1. Okay, so lambda here is less than 1. Okay. So notice that all of these random walks are symmetric. The probability of moving with an element is the same as moving with its inverse. Down. These examples. That's right. The mu G. Mu G inverse. And so then I have a question. Can we characterize random walks G and mu symmetric for which lambda is less than 1, or lambda is equal to 1 if you prefer. And it turns out that the answer is yes. And in fact, there's a classical theorem of Kesten that tells you the answer. It's a very nice answer that depends only on the group and not on the measure, provided it's non-degenerate and it's symmetric. So Kesten 1959 for his thesis. And we'll call this the amenability dichotomy. So if G mu is non-degenerate, and symmetric, then lambda G mu is equal to 1 if and only if G is amenable. Okay, so say a couple of things about this result. Firstly, as I said, the condition depends only on the group, not on the probability, provided you have these conditions. And also, it's very clean, there's no moment condition, no other hypotheses. There's no assumption. We're going to have to impose more assumptions in a minute, but in Kesten's result, there's no assumption that the group is finitely generated, anything like that. It's just a very general result. Okay, so I always, when I talk about these things, say what the amenability means in case there are people that don't know what it means. And even if you do, maybe it's nice to be told again. I've been told that audiences never mind hearing things they already know because they can then nod along wisely. So, groups. Okay, so this is a notion that goes back to von Neumann and his work on the Banach-Tarski paradox. And I'll just give the definition for countable groups, I mean, a more general definition. But let me give several definitions. So here's the original one. I think this is 1929. G is amenable if there exists a G invariant finitely additive probability measure on P of G, the power set of G, so on all subsets of G. Okay, and then let me give definition 2, which is a more functional analytic definition, due to Marl and Day, from my first 1950s. G is amenable if there exists a G invariant mean, let's call it M, that's in the dual of an infinity of the R such that M of F is always between the nth and the cert. And the invariant bit means that M of F of the function you get from, so the function you get from F by, multiplying the argument by G is the same as just the F. Okay. And then the third definition, which is the one I prefer, as I think it's easier to visualize. So this one is the formula in the 1950s. G is amenable if all epsilon greater than 0 and for all A contained in G finite. I mean, A is finite. There exists F contained in G finite. So these are just subsets such that if you take F and intersect it with it's translated under an element of this given set A, and compare that with the size of F, then this is greater than 1 minus epsilon all A in A. So the idea is that you're given your tolerance epsilon and you're given your finite set you can move things around by, then you can choose your F so big with respect to these given things that when you move it compared to the original thing, it doesn't change very much. And so sometimes this is true and sometimes it isn't. So let's actually write down some examples of types of group. So firstly, finite groups are amenable. Kind of trivially, you can just look at the first definition and just use normalized counting measure. Okay, so that's easy. And then set D. Well, let's think about Z for the moment. And let's not be easy on ourselves and look at the third definition. Let's look at the first definition. How would we get a finitely additive probability measure defined on all the subsets of Z. Well, you could say, let's take a big N to start with, and then for a set S, let's say we'll look at the intersection of S with minus n through to n, and then divide that by number of elements of that interval, so 2n plus 1. And then you like to take a limit. So I mean that's okay. So that's kind of close to being invariant. Okay. And if you, in the sense that if you translated that to set S by 1, you'd only change the measure by at most 1 over n, because you'd be at worst moving one element out and nothing in, or moving an element in and nothing out. So yeah, at worst you change it by 1 over n. And so, you know, you'd like to take a limit, and then you can't take a limit in the ordinary sense, but you can take a limit along a non-principal alpha filter. If you're not familiar with alpha filters, there's a really nice blog post by Terry Tao about them, which is well worth reading. But if we look at the third definition, it becomes much easier to visualize what's going on without, you know, kind of fancy things. You just say, well, so skipping with the integers, you know, I just have to be given my epsilon and some finite number of translates. I'll just choose the set F to be much bigger than the numbers in here. So much bigger that, you know, translating has a negligible effect. I mean, if this just consisted of the vector the number, you know, 100 to translate by 100, then I can, you know, depending on the value of epsilon, I can choose F to be, you know, numbers from minus a billion to a billion. So translating that by 100 has essentially negligible effect. Okay, and then so then it becomes much easier to visualize. And then, of course, if you think about the relationship between 3 and 1, why could definition of 3 imply definition of 1? Again, it kind of goes back to the, you know, ultrafilter argument. You could do this for, you know, a sequence, you know, epsilons of 1 over n, get a sequence of these sets to kind of work with, and then you take a limit on non-principal filter. Okay, so we get this, and indeed all the abelian groups. And then there's some algebraic results that allow you to go from abelian to nilpotent and solvable. And then somewhat later, I guess this is now 1970s, is a result of Hersch and Kesten that if you have a group with sub-exponential growth, then that's also amenable. Okay. Now there's a kind of subtle trap here. Well, maybe I'll kind of come back to after I talk about the non-amenable ones. They're non-amenable. So the basic example are 3 groups on K generators, where K is at least 2. And then any G that contains the 3 group on 2 generators as a subgroup, and any non-elementary hyperbolic group. So in particular, the fundamental group of any compact negatively curved manifold. So let's just think about the 3 group on 2 generators. And again, we can think in 2 different ways. We can think about the first definition And you say, well, if I had such a probability measure, then so let me in fact write this down if I can. Which is kind of cute. So, you know, if you had a probability measure P with these properties, you'd have P of the whole group be 1. Let's put M in that maybe. And then we could split this up into the identity, and then all reduced words that start with the generators of their inverse. The W of A is all reduced words that start with the letter A.
What M?
It's a supposed finite additive probability measure on the power set of B. And W, so W of A is all reduced words starting with A. So W of A is the set of G in F2 such that G is equal to A, and then whatever else. Okay, but then you could say, well, this is the same as another way of splitting up the three group and two generators would be to have all words that begin with an A, and then let's see, all words that begin with A inverse multiplied by an A. So so we get M of, let's say it would be A W A inverse. Okay, so if a word doesn't begin with an A, then I can put A inverse in front of it, and then I can multiply by an A to get rid of the A inverse and get that word. But then, because of the translation invariant properties of the measure, that's going to have the same measure as W of A inverse. And then I could do the same thing with B. Okay, so we can ignore these lines now, but okay, so then some of these two terms equal to 1, but these two terms appear here, so these are equal to 1, and by the final line, the last two terms here are equal to 1. So the right-hand side is equal to at least 2, whereas the left-hand side is equal to 1. So there's a contradiction. So that's one reason why three-group quantity generators can't be amenable. The other way, which is maybe nicer to visualize, is to think about the third definition. And if you think about a ball centered at the origin of the identity in the three-group quantity generators, most of the volume is at the edge. So even if you're just given your set here to translate by, it's just one generator. Moving it by one generator is going to change it by an appreciable amount. You can't get this ratio being close to 1. Okay, so there's two arguments why the 3 group on 2 generators can't be amenable. Okay, and so I said there was a slightly subtle trap in this when I was talking about sub-exponential growth, because you look at what I said for the 3 group on 2 generators, and it's very tempting to think it's because of the exponential growth. And if you had a group with exponential growth, then it wouldn't be amenable. But this turns out not to be true, because there are examples of solvable groups that are amenable. So there exists G solvable with, so solvable implies amenable with exponential growth. And there are examples that are actually come from dynamics. So I'll give an example. So if you just have, let's say F mapping the torus to itself induced by, let's just say 2, 1, 1, 1, basic cat map, then we can make a 3 manifold. So M is going to be T2 plus the insensible, and we're going to have an equivalence relation. So the equivalence relation is that x1 gets identified with f of x 0. Okay, so we're going to identify the endpoint of the interval according to the map F. And then this is a compact 3 manifold, and pi 1 and fundamental group is solvable and hence amenable, but it's known to have exponential growth. Okay, so that's some discussion of these things. So we've got this. We've got this very nice result of Kesten that's very clean cut. We've seen what amenability means. But remember, one of the hypotheses in Kesten's result was that the walk should be symmetric. So it's an obvious question: what happens if the walk isn't symmetric? So what happens to the amenability dichotomy if mu not symmetric? Well, the result says it fails. Okay? So even for your group being the integers, it's going to fail. So take G to be the integers, and you just put some drift in. So some bias. So let's say mu of 1 is 3/2, mu of -1 is 1/3. So you can still go in both directions, but there's a bias towards going to the right.
One.
Yes, sorry, 2/2, thank you. Not 3/2. Yeah, okay, so you can go to the right of probability 2/3, to the left of probability 1/3, and then yeah, you'll get lambda less than 1. Okay. Okay, but this kind of thing that I've written down here, I mean, not just specifically the answer of the integers, but most of that is really the only mechanism by which it fails. Okay, and so let me, next part I thought we'd be making that more precise and stating a theorem. At least provided you assume you're starting with a finitely generated group. So, so let's suppose we've got a random multi mu. Q is countable, and now it's going to be finitely generated. And we're going to think about its abelianization. So let me call that G ab. So that's going to be G quotient the commutator subgroup. And then that's going to, because we're assuming that G is finitely generated, that's going to be ZK, the some K greater than equal to 0, cross some finite abelian group. But really the finite bit doesn't really play any role. Okay. So, and if I don't want to spend time on this, but if K were equal to 0 and the commutator were finite, then we'd have the same result as in the symmetric case. Okay, that the lambda would be less than 1 if and only if G were non-amenable. Okay, so really we're interested in the case where K is at least 1. Okay, for 0, then lambda less than 1 if and only if G non-amenable. Okay, so here's the interesting situation. K is greater or equal to 1. So let's just mod out the torsion, and let's say that G bar is the abelianization modded out by the finite subgroup. So that's going to be TZK. And then there's going to be a natural projection homomorphism from G to G bar. Let's call that pi. And then that's going to push the original measure mu down to a measure mu bar on G bar. So formula. Explicitly, so mu bar of some well, integer vector m is going to be the sum over G in G such that pi of G equals M mu of G. Okay, then we've got a theorem. Which says that under the hypotheses we wrote down here. So maybe let's call these things start. Countable, finite, degenerate. I'm sort of assuming it's non-degenerate. So that's on the group. So maybe, yeah, maybe I should write down this explicitly. So assume that G is well, I won't know countable, but let's say finite degenerated. G mu non-degenerate. Then the lambda for the original group. So the thing to compare it with is not whether it's less than or less than 1 or equal to 1, but to compare it with the lambda for this abelianized group. So it's less than lambda of G bar mu bar if and only if G is not amenable. Okay, so that's the thing that the comparison you should be making. So in symmetric case, the comparison to make is that the lambda for your walk with 1. Here, if it's not symmetric, the thing you should be comparing is the lambda of the walk with the lambda of the abelianized group. And nicely, I mean, this is something that, in principle, you can calculate. Lambda in general is something that's hard to calculate. But if you just got a random walk on, on an integer lattice, then you only under nice conditions is something you can calculate. Okay. And so you see that this is why I said that the mechanism over there is the only way that things fail. If your group is amenable, then you have equality here. And so the only way this turns out to be less than 1 is if this turns out to be less than 1. And this being less than 1 is connected with there being some bias at the level of the abelianization. Okay, so let's try and be a bit more explicit about this this quantity. So there's some work of Stone from the 1960s. It says, well, think about, so this is more to characterize this quantity. So think about the following function. Phi from Rk, so K is the rank of the abelianization, the K over there, to R plus union plus infinity, and it's defined as summing over the group elements, and then it will be e to the inner product of your vector B with the abelianization of the group element multiplied by the value of the probability. Or in terms of the abelianization, it's this sum okay, and it turns out this is a strictly convex function and is a unique point where it's minimized. So there is this unique, let's call it psi in Rk, such that phi of psi is a minimum in Rk, and then
You're right. They include what you think pattern.
yeah, I mean, so if your group, if your walk is finitely supported, then it won't happen. But yeah. Okay, so then lambda d bar mu bar is given by the value of this function at the minimum. And this is equal to 1 if and only if mu bar is what's called centered. Well, all this statement doesn't require any moment condition. This condition actually requires an exponential moment condition on the wall. So, I mean, if it's finitely supported, there's no issue. If it's infinitely supported, you have you require some condition that there exists a C such that C greater than 0, such that sum over n into k e to the C norm n mu bar of n is finite. Okay. But anyway, even without that, there's there's some kind of explicit function you can write down that that gives this thing. And if you're thinking this looks maybe like something thermodynamic, yeah, you can interpret this in terms of weighted pressure, if you so want to do. Okay, so I wanted to try and say a little bit about the proof. Not the whole proof, but just some ideas and how amenability comes into it. So it turns it's obviously there's two directions. It's an if and only if statement. There are two directions. And it turns out that the direction, so let me well, I mean, if it's not finitely generated, then I don't really know what to do. I mean, and I think, I think the stone result implicitly requires it being finitely generated. But you can imagine really horrible examples of random walks on, on the rational sort.
I think let's do the count. just write sum comes to 1, and then this will be your measure.
Yeah, I mean, I don't know. I mean, there could be examples where it works, but as it stands, our proof only works for yeah, it's being finite generated. Okay, so let me just because I want to agree with the way my notes are, and otherwise I'll get confused. Let me change the statement to this one, it's the equivalent. So it turns out that the direction of equality here implies amenability is actually the easy direction, or at least it's easy in the sense that you can just reduce things to some previously known results of day. So it's kind of no harder than the symmetric case. So let's take that as read, and let's think about this direction, assuming amenability implies equality here. And in the symmetric case, this actually turns out to be the sort of easy direction. Here, this is just a lot more involved. So anyway, so let's go from here. So the amenable implies lambda equals lambda bar. So I'm just going to, for sure, I'm going to write this quantity is lambda and this quantity is lambda bar. Okay, so well, it's going to be enough because we always know that lambda is less than or equal to lambda bar. So just having lambda bar less than or equal to lambda is enough. Okay, the other inequality is automatic. Okay. And so there's a lemma which I won't. It's kind of the key thing, or a key thing. There's several key things, but there's a lemma that says if there exists a homomorphism H from Zk to strictly positive reals, such that sum over G and G mu star to the n of G H of minus I of G is less than or equal to lambda to the n for all n. Then we have the bound that we want, then lambda bar is less than or equal to lambda. And then we can actually replace this homomorphism with one on G, because so we're going to an abelian group. So any homomorphism on G is going to factor through homomorphism on Z. So we could say, let me find the color here. And let me just still call it H. So that, and then we've got H of G inverse. So you can phrase this just entirely in terms of G rather than the abelianization. Okay, so we somehow need to cook up some homomorphism on G to positive reals with this property. Okay. So how do we do this? Yeah.
So this level lambda is a number, not lambda of the group.
No, it's just lambda of the group. This is just Chiltern notation. Lambda is lambda of G and mu. Lambda bar is lambda of G bar mu bar. Just do it so I don't have to write so much.
So the last line will be equivalent to the equal.
Yes,
Okay.
exactly. That's if I can find this, then we're done. Okay, so how do we put this thing up? Well, the first thing you want to do is have some functions. So for G in G, well, define function, let me call it zeta superscript G, a real parameter T. And this is going to be the sum n equals 1 to infinity mu star n of G c to the minus n. So some kind of generating functions for these convolutions. And so this converges for c greater than the lambda for the group G. So I should say, I mean, that the growth rates for all of these independents of G will say all lambda. Okay, and now now you may need to do a little cheat, and this is kind of reminiscent of what happens in the construction of Kesten-Sullivan measure when you have the dichotomy into divergence type and convergence type. If it's divergence type, you just repeat. So this is the question at lambda whether the series diverges or not. If it diverges, all well and good. If it converges, you can put an extra factor in to make it diverge. So maybe you need to sort of cheat a bit and modify this, but that's not going into this. But what I want to do is, after a bit of argument, you can find a sequence. So you can find the sequence of Tn's decreasing to lambda, such that the limit as n goes to infinity. Oh, so it's a bit awkward. I've used n twice, but never mind. This n is not the same as this n. So what I want to do is compare the series for G and the series for the identity. So this lemma exists for G in G. And let's call this quantity A of G. And then you can, in fact, show that this has a relation, right? A nice relation. If we sum over elements of G, now for some reason they're being called S. So we've got G is going to be a fixed element, and we'll have mu star R S H S to the minus 1 G. So it's a convolution. That's equal to lambda to the R A to G. Okay, and now we're going to cook up this little h that we want out of the big H and the amenability of G. So define H from G to R positive by, okay, so H of, let's say, gamma is going to be the exponential. And now we're going to use the mean on L infinity that was the second definition of amenability, which I seem to be ignoring at the time, but now we're going to use it. So let's call this thing M. And the elements of L infinity of the group we're going to use is the thing that sends G to log of big H of gamma G over H of G. Okay. So I claim that this satisfies that inequality. So why is that true? So we'll start out with lambda to the n. So I'm going to use this identity. Says that lambda to the n is going to be equal to the mean of the functional, the infinity function that sends G to sum over S in G, mu star n of S, H, S to the minus 1 G and H G. Okay. Okay. So now what you want to do is just carry the m inside the summation. You've got to be a bit careful because remember m is only finitely additive, not countably additive. But you can you can take finitely many and go through, and then the limits work in your favour.
Excuse me, question. So here in the lemma, can you replace the star n of G with new bar star n of E of G? The standing over the case that you understand.
No, I mean, so here you want to have these individually. You don't want to kind of group them together. So I mean, you need to do it in this way. Yeah, you can't kind of bundle these together. Okay, so this turns out to be the sum S over G. We can take out S, and then it becomes M of G to S minus G over G. And then by comparing the Jensen inequality, we can down this below by so it's going to be exponential m of G goes to log of H. Right, 1G over G. And then that's the correct definition for H of S inverse. So this is And that's the inequality that you wanted for the lemma over there. So that's kind of the essence of the proof. I mean, with lots of the details omitted. So I've got another, what, 20 minutes? Okay, so next thing I want to talk about is as a consequence of this, which is ratio limit theorem. So if you kind of got lost or bored by this talk about the proof, you can hopefully now snap back into the talk, because we're going to reset a little bit. So, in an ideal world, we're talking about the growth rate, but in an ideal world, you'd like to be able to say things about, this thing for any value of G, and this convolution, so in other words, probability of getting from identity to G in n steps, so it's an asymptotic as n goes to infinity. And we call that a local limit theorem. But there are not many cases where this is known properly. So obviously it's known, for kind of abelian groups and Laplacian groups, and then so there's that world, and then there's the result of hyperbolic group, pre-group hyperbolic groups. But in general, it's a bit mysterious. But what might be easier is to look at the ratios. So compare this thing for G with the corresponding quantity for the identity, and ask, does this have a limit, and what is this limit? So first of all, there's the obvious problem that this thing on the bottom might be 0 some of the time. So let's just make a hypothesis that this is eventually positive. Okay, so we can call that aperiodicity. Or, I mean, if you don't have it, you could look along some appropriate subsequence. But let's just say mu is aperiodic if there exists some n0 such that mu star n of E is positive for all n greater than equal to n0. Okay, so about this ratio result, there's another old result of Ave from 1973. That says if G is amenable, mu is non-degenerate, aperiodic, and symmetric. So we're back with this symmetry condition again. And then this limit always exists and is equal to 1. So the limit n goes to infinity, G, n of G over mu star n E is equal to 1 for all G in G. So again, there's a question of what happens when it's not symmetric. And we can use our first result to answer this at least in the finitely generated case. this, well, I guess we proved it in 1970, 2023, it's about 50 years later. Right. So if the amenable and mu is non-amenable and finitely generated, mu is non-determinate and aperiodic, the no symmetry condition, then the limit still always exists. But it's no longer one in general, it's equal to the following thing. Where this psi is the psi that appears before, it's a value where this function phi has its minimum. And this is the abelianization of G, or the torsion-free part of the abelianization of G. So you get this formula. If the abelianization is finite, then you still get one. It's the limit. Okay. And furthermore, so if I call this formula dagger, if dagger holds, so this is the effective thing in G, furthermore, dagger implies that G is amenable. So if the ratio limit is of this form, then the group has to be amenable to start with. Okay, so I kind of promised.
Okay, is it amenability, you use this for all G or just generating set? Is it sufficient?
Oh, sorry, what was the first bit of the question?
So this is the last implication. So here, do you have identity for all G or say for generators? Is sufficient?
Oh, I don't know. I mean, I don't have an obvious argument that would say knowing this for the generators would tell you it for the whole group, but maybe if you know enough things, it follows. But yeah, that's a good question. I didn't think about that. Okay, so I promised at the start, or at least one of the biblical promises that people give in talks, that I might talk about some dynamics towards the end. So let me do that now. So I mean, we didn't start working. We work, with dynamical people. Well, Rhiannon is more and more representation theory type person, but it comes from dynamics and logic theory, and we didn't just start working on one group. What we're actually thinking about was a different problem initially. So this amenability dichotomy that Kesten introduced turned out to have lots of variance. So there's results of Gorchuk and Cohen about what's called co-broken groups. There's results about books about spectral geometry and bottom perspective of the Laplacian. And then that's for interpretations for tiny groups in terms of physical experiments. And then you can relate that back to entropy in both orbits. So think about the following problem. Suppose you've got, let's say, phi t from M to M is the transitive velocity flow. And then the topological entropy, so that's called that H of phi, so this is the topological entropy, is given by the growth rate of the periodic orbits. So it's the limit as t goes to infinity, 1 over the log number of gamma in, let me just say here, orbits such that L gammas in each period is less than or equal to P. And this really is the limit. Well, let me assume that we're remixing. Well, it doesn't matter just being limit, but no, that's it will be remixing eventually, but let's not worry about that. Yeah, it's a limit. Okay, and suppose then that we took a regular cover. Look to the lifted flow. You could ask about the growth rate of periodic orbits up above. Then you have to be a bit careful because if you've got one periodic orbit up above, then you can just translate it around by the group. So let's just say you fix some compact region up above and look at orbits that intersect there. And take the growth rate. Or you could talk about periodic orbits down here that lift the periodic orbits up above. But either way, you'll get something, let me just call it a to pi tilde, that's less than or equal to a to pi. And so it's a question of when you have equality. And if it's a geodesic flow, then you're in a situation where the amenability dichotomy holds. I mean, so if this were like a compact hyperbolic manifold, then it would just follow from old results, and then more generally, there's lots of people who work on it. Graham and I worked on it. Francois Calvo and various people worked on it, part of Shapira. So there's lots of results in this kind of symmetric setting. A lot down earlier. So let's just say if I T geodesic flow over the curved manifold, then H pi tilde equals H pi if and only if G is amenable. So then this is the question of what happens if you don't finish a geodesic flow, if it's just a general Anotov flow. And then the dichotomy is fairly false for similar reasons to the random walk case, so even at the abelian level. So you can think about abelian covers where there's some drift, some patterns going in some direction, and so the number will go down. Okay. So Rhiannon and I were thinking about this, and then we kind of hypothesized in a really kind of blue sky sort of optimistic way that it was the only way, if you're in the amenable setting, if you're covered amenable, the only way things would drop is if at some intermediate abelian cover, it drops because of some drift. And that turned out to be true. And so there's a theorem that says, well, provided this flow is countable. So I'm going to try and write down the result in the last few minutes. So theorem Yes. Right, so you want to have, as over there, transfer and also flow. So phi t trans and also phi tilde of t transitive. And then you have that h phi tilde is equal to h of, let me call this phi bar, if and only if g is amenable, where this is the growth rate, the corresponding growth rate of a periodic orbits on the largest abelian subcover of m tilde. Okay, you've got m tilde up there, m there, and then in between you've got a maximal abelian subcover. So that's a statement. And again, this is something you can hope to, this abelian number is something you can hope to understand by thermodynamic formalism. So we had the paper on this, was accepted, but in the course of the referee report, the referee commented that it was surprising that there was no result like this known for random walks, which was supposed to be an easier situation. So, so that's basically why we started thinking about the random walk case after the dynamical case. And I think that's where I'll stop. So thank you very much.
I wonder if there's a chance to realize your first result for the case of prior graph. So your prior related group acts on some graph page, and you want to have a criteria of amenability on the prior graph, or rather taken similar formula for lambda prior graph.
Yeah, I mean, so there's certainly in the symmetric case, there are versions of it for of a graph. Yeah, so I guess the question, how do you formulate? I mean, it'd be nice just to think about this just for maybe just a graph. And then yeah, I mean, I would imagine it would be some similar kind of statement.
I think for general graphs, it's slightly, I cannot quite imagine how you would formulate the situation, but for Schreier graph, you have kind of enough symmetry. But for general graphs, I mean, how do you somehow see this measure in different vertices? How do you you don't want the uniform one?
Yeah, I mean, I guess I was kind of thinking about covers again, but that's but anyway, yeah, I mean, certainly food for thought. Thank you.
Yeah, I also wonder, so in the case of technology, what would be this kind of result for the quantity? Is there a hope to kind of compute h of phi tilde in terms of h of phi and say lambda or g or something similar?
So the other thing I know coming in this direction is that so this results of the Rhiannon Dougall and also the results of François Salvo and others. This is in the symmetric case, but if you had a family of non-amenable things, would the growth rates become arbitrarily closed, or would there be a gap? And that turns out again to be a group theoretic property predicted with this Cashman number representation theory. So that's a way of reflecting, but I don't really know the answer. I think actually working at getting exact numbers is probably really hard. And I think the best thing we think at the moment is just kind of positive properties of how families behave, whether they're banded away or things like that.
And I have to repeat, you tell me explain again what is psi and the corresponding function means.
This is one.
Yeah, and you tell why this minimum of these functions could actually show some stuff about these eigenvalues of them. How do you see it?
Yeah, I'm not going to be able to like things like that well, but so you've got this third function that's well, I mean, if we're thinking about this CB, I think maybe we could just think about this. Like that. So one thing, I mean, so okay, so think about taking I mean, so this is kind of more primitive, if you like, before that theory. But yeah, I mean, you should. Okay, so I mean, if you thought about if you suppose to make things easier, your walk is finitely supported, then you could take the support and make a full shift. And then you could make the probability into a function on the shift. And then this would be like the exponential of the factor of compounding the functions. So when you start differentiating, you're going to get to integral. And the situation where the minimum is 1 is where that occurs at 0, where size equals to 0. And you just have the corresponding integrals, which would just be just giving just be giving you 0, which would correspond to things somehow big center.
Thank you.
Any other question? Is there a way that co-amenability can be seen in terms of lambda?
So what can we say?
Co-amenability of a subgroup. So H being co-amenable.
Probably. I mean, when we get into this, I'm not so familiar with the results. There's a big paper by Barbara Shapira, Rhiannon Dougall, and Coulon, and someone else whose name I can't remember. So apologies to them if they ever watch this on YouTube. Which is in memoirs of the AMS, which it's in the countable, I suppose, kind of lots of more sophisticated things. Maybe that's a good place to start.
Could you write the name of?
Including the name of the person I can't remember. So let's see. So so I mean the authors are going to be so one's Coulon. And again, apologies if I misspell these things. Dougall I can spell. Shapira, Barbara Shapira. I'm very embarrassed, I can't remember the full person's name, or where they could come, but class excellent. Um, it's in memoirs. That's the AMS. Tuffy, yeah. Well, there's the alphabetical position.
There are no more questions. Let's move to chart again.
Maybe a quick announcement, we want to organize to get together with our husband and friends. So, I would like to tell you if we cannot in the beginning of September. And that we, the way, please, take it on. Yes.